Hello, everyone. So today we're going to be covering a little bit of a grab bag of topics. So we're going to be focusing on state functions and equations of state. So these sound like some really complicated forms or words, but these are really going to be the bread and butter of how we're going to move on with physical chemistry. So over the last couple lectures, we've kind of walked through how one builds up a series of equations, such as the ideal gas law. But I want to take a step back and more focus in on why we want to use the gas law and why it matters so much. So when we're talking about state functions and equations of state, what we're really going to be talking about is the bread and butter of how we describe a system. So a good place to start is state functions, which is just a complicated way of talking about a property that defines the current state of a system. So these include classic state variables such as the amount of substance, so the number of moles, the pressure of the system, the volume of the system, the temperature of the system. These four are great and classic variables simply because I can go out there and measure them. And that if I know a subset of these, I can perfectly define the system I'm looking at. But it turns out that state functions aren't always just measurable quantities. They may be some things that are a little bit more intangible. So we have still combined state functions like density, which is going to include some of the intrinsic properties of the substance plus moles and volume, but it also includes things like entropy, enthalpy, and free energy, which really will help define more of the behavior of the system. And this can be really valuable when I want to predict how a system will behave. I'm going to really need to start with these state functions. But there also turns out to be another really cool property. Specifically, if I'm looking at something like a simple gas, it turns out that as long as I know three of these functions, three of these state variables, I can theoretically calculate any of the other ones. And this is incredibly powerful. And the biggest way that we do this is with something called an equation of state. So an equation of state is just going to be a way to define a state function, for example, pressure, in terms of three other variables. So the classic one is I can define pressure in terms of the number of moles, the volume, and the temperature of the system I'm looking at. And so this can be incredibly useful because it turns out that sometimes I may only be able to physically measure three of these variables. So if I have an equation of state that lets me get one of these variables from another subset, it becomes incredibly powerful, especially when we're talking about difficult to measure state properties such as entropy, enthalpy, and free energy, which can be much trickier to work with. But it's also worth noting that it turns out in order to get a very simple and useful equation of state, we often need to make a series of approximations. For example, like we did last time when building up the ideal gas law. But one of the other things that we also need to make sure we define is going to be a series of variables that don't quite uh, lend themselves to a simple numerical description. And these can be things like phases. So if I'm going to be trying to build up an equation of state for a system, I'm often first going to need to define something such as its phase. So the three major phases we're going to be talking a lot about this semester are liquids, solids, and gases. There are some novel phases out there, but they're going to be kind of beyond the scope of this class. And it turns out that the best understood of these three are going to be gases. So we're going to be spending a lot of our time focusing in on this gas behavior. And the big reason why we're going to be doing this is that gases are going to be very dilute, which means that I have to worry much less about atom-atom interactions. And we love simple, especially as a starting point. And this means that they're inherently more behaved because there's less noise from those interactions. So Turns out that because of this easy behavior, this is where most of our early chemical equations were derived. It turns out some things that do end up helping are the fact that, well, early research money also helped drive this, and having a solid that produces a gas was a big incentive to understand gas behavior. And if it could be used for war, well, military funding is always a good standby. But once we have understand the phase of a material, we can essentially try and perfectly describe the state of the system. So again, this is going to be similar to our state variables. It's just that they were able to um, if two systems contain all of the same state variables, they're said to be in the same state. And what we're often looking at is, again, these state variables, which is going to be simply a list of all of the physical properties. And if I have uh, uh, all of the physical properties that essentially can perfectly describe the state of the substance. So if I've got two identical substances, they're said to be in the same state, and they should share all of the same state variables. So it turns out that a gas can be perfectly described by only using a small subset of our state variables, specifically our good old friend volume. So this is going to be, well, the physical volume occupied by the substance. I can measure this one manually. But it's worth noting that this is going to be a size extensive property, and that it depends upon the size of the sample. And this is important to note, is that the state of a material can indeed depend upon its size. So if I have two objects of identical composition but different size, they may not necessarily be in the same state. We also have a second size extensive property, which is going to be the moles of the substance. And again, I can determine this simply by knowing the identity of the substance, which gives me the molecular weight, and the mass. Now we also have slightly more complex ones, like pressure. So this one, as we saw last time, is size intensive. It doesn't depend on the amount of the substance I have. And its measurement is often a little bit trickier. This was traditionally measured using a barometer, which essentially just measures how much force is applied to a known area of mercury, because mercury, being an elemental liquid, is quite well behaved. And then finally, we have temperature. And as we saw last time, temperature is kind of a messy state variable. So first of all, one of the things that's great about it is that it is size intensive. And as we saw last time, it's often best described as as a measure of the amount of energy inside a gas, specifically the kind of kinetic energy. As we saw, a clear relationship in between the temperature of a system and the amount of kinetic energy present by a simple 3/2, 5/2, or 3 kT, depending on the identity of the substance. Now, this gives us four variables along with the identity of the substance, including the fact that it's in a gas, that can again perfectly describe our gas system. But it turns out that I only need n-1 variables to perfectly define the system. And this gets into this idea of state equations, because I should be able to generate a state function or an equation of state that perfectly describes volume in terms of the other three. Now, one of the tricks is when we're trying to generate these equations of state, this gives us four variables, so we often want to fix one set of variables or another. And it turns out that one of the easiest variables that I can affix is simply the amount of the substance. And this leads us to an important set of conditions that we can try and compare. So we often like using limiting conditions when we're describing equations of state. And so it's worth noting that we can divide our systems into two major types. The first of which is going to be an open system, where literally this can be described as a beaker open to the air, where I allow particles to move in or out of the system. So this means that n is variable. And well, that's kind of annoying, because if I want to perfectly describe my pressure, then it turns out I need to know n, v, and t, so I don't want n to change if I can avoid it, especially for a fixed volume. So An alternative is going to be a closed system. Cap off the system, don't allow any particles to enter or leave. This gives me a fixed amount of n, and this is actually fairly nice. And it will simplify our descriptions of our system immensely as we go throughout the semester. So we're typically going to be working with closed systems as they're a little bit simpler and easier to be and much easier to describe. So this essentially leaves us mostly talking about the behavior of our system in terms of pressure, volume, and temperature. And we're going to use this a lot as we move throughout the semester of looking at the relationship in between these three variables. So if I'm working with a gas, one of the easiest ways to relate these three variables is with the ideal gas law, which we've been able to describe multiple times. But again, in practice, this gives us four variables. And even if I work with a closed system, this essentially is going to give me three variables to work with. And I'm usually going to want to fix two of these variables, typically number of moles and something else. So working with a closed system. So the classic approximations we're often going to use is looking at isothermal conditions, where I fix temperatures, so constant temperature. Isobaric conditions, constant pressure. Think about the unit of pressure, bar. Or isochoric conditions of constant volume, where I work with constant volume. And one can think of this as when I have a free gas, it's going to exist somewhere on this three-dimensional curve of pressure, volume, and temperature. And by keeping one of these last variables constant, I go from a full messy three-dimensional picture, which I have a hard time imagining or describing, to a much simpler two-dimensional line graph, where I'll have a simpler relationship in between volume and temperature, pressure and volume, or pressure and temperature. So this gives us our classic Avogadro's principle, Boyle's law, and Charles' law. They essentially just work under either isothermal, isobaric, or isochoric conditions, or again, open and closed systems. So one of the other really useful things that I want to talk about the simple ideal gas approximation is that it turns out that it can be applied to just simple subsections of our gas. So we can actually write up an ideal gas law for each component of a gas mixture. So for example, if I'm looking at just the pressure of O2 in the atmosphere, this is going to be related to the number of moles of O2 and the total volume and temperature of, say, the room I'm looking at. And this actually becomes rather nice because since I know that moles are going to be an additive quantity and temperature and volume don't change, it turns out that the pressure can also be related as a sum of the pressures and the pressures, which then putting in each of the individual ideal gas laws can also be expressed as a sum of the number of moles times the total RT and V. If it makes you feel a little bit better, you can imagine pulling RT over V out in front of our sum of components. However, this is often most commonly written as essentially a mole fraction notation, where the pressure of each individual component can be given as the total pressure, again, this total N RT over V, times the mole fraction of the component in state I, say Ni over Nt. So again, this can be a very useful way of describing all of the components of a system simply based on the mole fractions and the total pressure. And so again, this is a really nice way to convert in between partial pressures and mole fractions. And a good example of how this can be very useful is, say, I'm looking at an atmospheric system where it's mostly composed of oxygen and nitrogen. And I might want to figure out the total or the partial pressure of each of those components. So as long as I know that the mole fraction is 21% O2, I can quickly figure out the partial pressures of each component. Because with the total pressure of 1 atmosphere, I have a partial pressure of O2 of 0.21 atmospheres and a partial pressure of N2 of the remainder of 0.79 atmospheres. Again, showing that the atmosphere is generally mostly nitrogen, higher partial pressure, and a minor component of O2. And also, this is fairly useful because as long as I'm under this ideal case, I can treat each of my gases independently, just based on this, on the fact of as long as they obey the ideal gas law, I can more or less use the additive property of the number of moles. However, one of the things I may want to make sure that you're aware of is that we often run into a problem when working with gases, and that's simply the fact that I don't like working with size extensive properties. Things like volume and the number of moles. These can be quite problematic to work with when I'm working with something like the atmosphere. So it's often very traditional to try and convert size extensive properties like volume and moles and combine them to make a size intensive property. And this is also something useful to be aware of as we go forward. That if I take the ratio of two size extensive properties, I generate a new size intensive property. So the classic one we like to use is molar volume, which is just the ratio of volume and moles, or again, could be thought of the volume occupied by 1 mole of gas. And it turns out that this is just going to be equal to RT over pressure. So again, just a slight rearrangement of the ideal gas law. It's also not uncommon to take the inverse of molar volume, which is literally just going to be concentration. And again, one of the things that's important to note about concentration and molar volume is that they're again going to mostly be independent upon the identity of the gas and only really matter upon temperature and pressure, for much the same reasons that we saw temperature and pressure themselves not depend upon the identity of the gas, because most features that depend on molecular weight kind of cancel out as we go along. So in general, our molar volume of our gas is often going to be given with reference to one of two conditions, because again, we often like talking about standard temperatures and pressures. So if I use the standard temperature and pressure notation, this refers to 1 atm and 0 degrees C. So this is actually very important to note. As the class goes on, anytime I talk about STP, I'm going to be talking about 1 atm and 0 degrees C. So not bar, not Kelvin or Fahrenheit, not room temperature, but again, freezing and 1 atm. This shouldn't be confused with one of my favorite notations, which is standard ambient temperature and pressure, which is 1 bar. So this is our classic SI unit, and 25 degrees C, or our classic room temperature. And what's actually very cool is that any gas is going to have a specific molar volume under each of these conditions. With under STP, a gas occupies about 22 liters per mole, whereas at SATP, it's going to be closer to 25. So these are actually going to be some fairly useful things to know as we move on. And this more or less brings us to our quick summary of ideal gases. However, next time we have to acknowledge the fact that everything isn't always hunky-dory and ideal. So we are going to need to develop some equations of state that describe more complex conditions. Until then, take care.